I have mentioned this before, you get to keep this. So you should write on it, so you have it for your cumulative final. The fill in the blanks are bottleneck. I gave you 1 point for drift, but understand that it's not just a drift event, okay? It is a bottleneck event. So you got 1 for drift, 2 for bottleneck. Founder effect, inbreeding depression, and over dominance. Okay. On 30, A is possible. If you add up the numbers, they add up to the frequencies of the individual alleles. It's possible. If you then do the math gives you a number of 0. Does anybody need to see the math? I'll show you the math on the next one anyway, and so we'll be sure to know how to do this. Which means, of course, they are inherited independently, and you needed to say that because that was part of the question. Inherited independently. For B, .30 for the frequency of big A, big B, times 0.45 for the frequency of little a, little b. Now, that was 0.30. This equals 0.45. Big A, little b was 0. Little a, big B was 0.25. And the question was, obviously, is this in leakage disequilibrium or not? Well, I had a couple of different people say, you can't have a 0. Well, you can have a 0. If it's in complete linkage, you can have a 0. Okay, especially if the numbers add up. Well, there's 0.30 for big A. For big A, 0.30. Okay, and for big B, we've got 0.30 plus 0.25. Is that 0.55? Sure is. These numbers are actually perfectly fine. And of course, if you do the math, then it is 0 times 0.25. Well, this is 0.135, and clearly this is 0. The value is 0.135, which means they are linked. Okay. And in the last one, C, it's not possible because big A, big B, and big A, little b are collectively 0.5 together, which is not equal to 0.3. Yes? Anybody got any questions on the disequilibrium coefficients? Okay. Complete color blindness. People on the Pingalap Atoll. Good try by many of you. Some of you actually got it on the nose. Okay. Most of you got the fact that it started with a P, which was at least something. Okay. And you had to say something about what kind of event led to and these guys went through a genetic bottleneck. Hurricane in the late 1700s reduced the population down to 20 people. Okay, now if you said you reduce it down to a few people, I kind of let that slide. One of which was heterozygous for this, and therefore the population on the island has a much higher frequency than the world as a whole. Okay, all right. Now, we've done many of these. For purple, 2 times 1214 is 2428. 2428. 720 light blue mean there's 720 big C alleles and 720 big C2 alleles. Okay. And then white 670, that gives you 1340. Okay. And if you add these up, it's 3148 and 2060. And you add these up, it is 5208. If you add up the total of the individuals, by the way, it is 2604 for the total number of individuals. This is twice that. So you know these numbers are correct. Okay. Frequency of C1 equals 3148, that number there, divided by 5208, total number of alleles. That literally gives you 0.6. And if you went with 0.6, I was fine. You could be finer tuned than that, but 0.6 was fine. Okay. That, of course, means that the frequency of C2, you, of course, can do the math if you want to. 2060 divided by 5208. And you should, of course, understand that that's going to come out to 0.4. Anybody need clarification? There were some issues with this, okay? But please understand that we did this as examples in the classroom. You had this on your assignment. I did one more for you last week, week before last, before the test was done. And so I'm not doing anything different than what I've done before. Okay? All right? You with me? Okay. So the expected numbers, all right. So the actual numbers again were purple, 1200, purple, 1214, light blue, 720, and then white, 607. So these are the observed. The expected values are going to be 0.6 squared times 2604. 0.4 squared times 2604. And then, of course, 2. Some people, I don't know why, but there were a couple of you at least that forgot that this is 2 times this value. It's 2 times 0.6 times 0.4 times 2604. If you do this math, it comes out somewhere in this range, 937, 1250, and 417. Your numbers will vary depending on which numbers you actually use, whether you rounded off to 0.4 or kept it at 0.396, okay? But it'll be somewhere in that range, okay? Depending on how much you rounded it off, okay? Yes, yes, all right. Okay, Hardy-Weinberg equilibrium, nowhere close. 937 is, of course, very different from 1214. 1250 is very different from 720. 417 is very different from 670. This is not in Hardy-Weinberg equilibrium, okay? Nowhere close. The expecteds do not match the observed. Who's at a selective advantage? Well, remember that who's at a selective advantage is whoever has observed numbers greater than the expected. That would be purple and white. Purple and white. What's the likely selective pressure? Well, the most obvious selective pressure when you're talking about flowers would be pollinators. And understand, if you had somebody preferring purple, purple mates with purple gives you purple. That's it. If you pollinate a purple flower and pollinate another purple flower, you will get more purple flowers because they're all C1. Yes? And if you have another pollinator that prefers, yes, thank you. And like I said, I was wondering if that wasn't the disconnect report. And I don't know. Yes. I figured that was it, and I tried shoving it in there, but that's obviously not the right place. Okay. Actually, maybe if you will show them too. So I've been trying to figure out because it looks like this game shouldn't be like that. Okay. Well, like I said, somebody keeps coming into this room and messing with it majorly, and so I don't know. And it's really frustrating to come in here and not be able to use the screen. So, but thank you for coming up so quick. And I don't think it's honestly. You're the only one teaching in here. There's like another professor in here. I think they have the same problem. Or we have tickets from them. Oh, well, too. So it's somebody that's using it externally. Well, that's annoying. All right. Anyway, what was I saying? Oh, and so Understand too, if you have another pollinator that prefers white, if you mate white with white, you get white. Okay. So if you have two pollinators or even one pollinator that prefers purple and white, you're going to get more purple and white. You are. Okay. Because that's what you get when you mate purple with purple and white with white. Okay. So that's the answer. Any questions on that one? Okay. On 33A, please understand that positive selection is not simply a mutation that is beneficial. That is not what positive selection is. Positive selection is actually on the mutation rate. So this is a selection where a higher mutation rate is actually favored. That's what that is. Okay. Higher mutation rate is actually favored. And the example I gave you was the genes for antibodies, where you mutate the genes for antibodies that actually makes it possible for you to produce antibodies that recognize an antigen you weren't recognizing before and fight it off. So that's actually not a bad thing in that case. I threw out B. That's why everybody has at least a +3 on their paper. Okay. I threw out B. All right. C. Having said that, wow. That did not write at all. I mean, not a single bit of ink came out of it. This is the formula. V is the additive. VA is the additive variation. D is the dominance recessive. That's traits controlled by single genes, as opposed to the additive, which is multiple genes. Okay. And then the E is the environmental. Okay. And for those of you who did this correctly, it was simply 4 divided by 26, which equals 0.154. Is that it? Okay. It was just that it wasn't hard. It was just putting numbers in the right places. Okay. For those of you who got it correct, you still got those points. Okay. Still got those points. So even if you got it correct, you still got 3 points added onto your score. Okay. I basically threw it out and gave you credit. Okay. What's codon bias? It's when you have, as you know, 64 codons, right? But only 20 amino acids, which means you have some amino acids that are coded for by as many as 4 or even 6 different codons. Okay. Now, assuming that all of the codons were as equally efficient, you would expect them to be equally distributed. They are not. For any given amino acid that is coded for by 4 or 6 codons, okay, or 3 or 2 or whatever, usually there's a codon that is the most abundant one. That is the codon bias. Why is it the most abundant one? Because apparently you make more tRNAs for certain codons than others. And it is the anticodons matching up with the codons that make the translation more efficient if you have that codon. So although technically, if you were to mutate from one codon to another for the same amino acids, it would be silent. It's not quite silent because of translational efficiency, because you are apparently making more tRNAs for certain codons than others. That's codon bias. Okay. All right. And then number 4, this was basically remembering what increases variation in populations. That table. Okay. Even in the face of strong directional or stabilizing selection, what could still maintain variation? More than expected frequency dependent selection, more than expected disruptive selection, mutation itself maintains some variation, and then of course immigration into the population, gene flow. Okay. For instance, We had an example like that we talked about, where there were water snakes on the island. There was strong selection for non-banded forms, and yet banded forms were still found on the island. Why? Immigration. There was a continuous flow of genes into the population that maintained that variation in that population. Yes, yes, yes. Questions, comments? Okay, extra credit. Why doesn't selection eliminate all recessive lethal alleles from the population? The answer is, of course, because you can have heterozygotes. Because if you're heterozygous, the dominant allele will mask the effects of the recessive lethal allele. Simple as that. The second part of this question is a little bit more difficult. Why doesn't selection eliminate all dominant lethal alleles? And of course, the answer is because not all of the dominant lethals that are out there kick in before you can reproduce. If you can get to reproductive age and you're still alive and you can reproduce, technically speaking, that dominant lethal allele can be passed on. Okay, I gave you as an example Huntington's chorea, which kicks in about age 40. Okay, all right. I mentioned certain cancer alleles that may kick in, okay, when you're later in age, that kind of thing. Okay. Benefit to being heterozygous for sickle cell, malarial resistance. Benefits to being heterozygous for cystic fibrosis, resistance to typhoid fever. Why for some of the mimics does it make sense that only one sex will be involved in the mimicry and not both? It's because the more mimics you have, the more likely predators are to eat the mimics and think, oh, that's a good taste. Okay? Yes? You with me? So if you have just one sex doing the mimicking, then you reduce the number of mimics by half. Okay? And of course, who's the one that mimics? It's the females, because the females are, well, more important. You lose a male, other males with sperm. Sperm are cheap. Okay? You lose a female, you lose not only her, but all of her potential offspring. Okay? All right. Unusual about chromosome number 4, there's no crossing over, which means all the alleles on that chromosome are inherited as a unit. Does anybody have any questions about any of the Scantron part of the test? Okay. So they really screwed it up, huh?
Yep. Yeah. They gave the last time they screwed up something inside here.
Goodness. Is there some way to stop that person, whoever that is?
I wish.
Yeah, wouldn't that be good? So, all right.
Do a little more tripwire right here.
Yeah. We need a ring camera on the outside of the door.
Yeah, so, you know, but change that cable to maybe electrical, that way we'll get shoved up.
Would be good, wouldn't it?
Who complains about getting shocked?
Well, I'm glad. I felt kind of stupid because I thought, well, surely I can figure this out, and now I don't feel so bad that I couldn't figure it out. So. Just one thing. Okay, we had just started talking about chapter 10, and I had discussed so far the giraffes and their necks, and how the hypothesis, of course, for many, many years was giraffes' necks over time got longer and longer, There were and understand, again, there would have to have been mutations to make the neck longer, and then another mutation to make it a little longer, and then another mutation to make it a little longer. Now, do you suppose the giraffe's neck is an additive trait? Length of the neck. Oh, yeah. Christiana's up here nodding her head, yes. And of course, that makes sense because that's basically like height, right? Length of neck, multiple genes. So it could have been mutations in multiple genes, and that probably could happen more rapidly than a single gene, okay? And so over time, the neck got longer and longer and longer. Of course, the idea was that, oh, they must have gotten longer because they feed on acacia leaves and acacia trees are tall, and this made it easier for them to feed. And what did we find out? That was not likely the case, partly because if you look at males and females, there's sexual, do you remember the word? Dimorphism, okay? And understand anytime you see sexual dimorphism, then there's probably some sexual selection going on, where females are picking males based on these traits, okay? Yes, yes, okay? And so understand that you can have a nice hypothesis, but in order to know for sure, you have to do what, which you always have to do in science? You have to test it. You have to test it, okay? All right. So now, we can't test it directly. We can't go back and watch the whole process in order, but we can see what females in the giraffe populations do. We can see what males in the giraffe populations do. And I already showed you them fighting with their necks. And who wins? The one with the bigger, basically bigger overall body, but that means longer neck as well, okay? And by winning, that means he gets to mate with the female that's watching, okay? Now, again, why does the female also have a long neck? Because the genes are still there. They still get passed on, okay? It's just that testosterone probably enhances the effects of those genes. Yep, yep. You with me, everybody? Yes, go.
Could selection for giraffes now be to reach higher now that they're...
Okay, and then I went on to say, understand that having a longer neck does indeed make it easier for giraffes to feed on leaves higher up in the acacia trees. So just because an adaptation might not actually be for what we thought it might be for, that doesn't mean it can't help for what we thought it might be for. Yes, that's what I meant to say. I had to think about what I just said there for a second, okay? Yes, you with me? And this is where I brought up the idea of pre-adaptation, where one adaptation benefits you in another way. For instance, after I said that, then I mentioned feathers, okay? Because I told you this more than once now, once we knew to look, we look back at old dinosaur fossils and we find feathers associated with a number of different raptor species. They were faint, but once we knew to look, we could see they're there, okay? And if I asked you in today's world, what are feathers used for? Your answer would probably be flight. But is that what they were originally used for? These big raptors had no chance of getting off the ground, okay? The feathers were short, they were on the limbs and on the body and on, and it turns out, of course, that therefore it was likely for thermoregulation, warmth. Okay. Again, we can't go back and test it, but we do know that velociraptors were high metabolic organisms, very, very efficient predators. Okay. And this probably just made them more efficient. It was selected for. Okay. Yes. Yes. So feathers probably evolved for warmth, but that was a pre-adaptation for later on evolving flight. Yep. So that's where I left you last time. Let me go through the 4 things here. I'm hoping that they'll get this fixed by the time I need the screen. Okay. Understand that when we talk about adaptations, every difference you see between populations, is it true that every difference you see between populations must be adaptive? No. Okay. We've already said that there are other, okay. I did say you should work with a selectionist mindset, meaning if you do see differences, you should think first, those differences are probably selected for in different populations. But we also know there are other ways to change gene frequencies. Drift, immigration, yep. Okay. And just because there's a spot in a slightly different place in this population than in this population does not necessarily mean it is adaptive in some way. So don't be thinking that every difference has to be adaptive. Okay. All right. Now, I also pointed out that something that's adaptive may be somewhat maladaptive in another way, because I showed you giraffes trying to drink. Now, what is it, however, that keeps the giraffe's necks long? It's because the advantages outweigh the disadvantages. As long as the trait improves your fitness, even if it's not great in another way, as long as the benefit outweighs the cost, that's still going to be selected for. Okay. All right. And then last but not least on my list of 4 things there at the beginning of this handout, adaptations are not perfect. We already said evolution is not about moving toward perfection. Adaptations are not perfect. Why is that the case? Why can't you perfect adaptations? Well, it's because any new trait came from a pre-existing trait. You can only work with the genes you have. I've already made the point pigs will never fly. And if pigs ever evolve to a point where some of their descendants actually do fly, they won't be pigs anymore. Okay. You with me? Did I see some light?
Yes.
Okay. So you with me, everybody? You can new traits come from pre-existing traits. Okay. But do remember, we talked about how important gene duplication may be, that having genes that get duplicated, okay, means you do have new genetic material to work with. Yes, we talked about that before. Okay. All right. Now, one last thing before I hopefully jump onto the screen here. Good, thank you. Perfect. On page 376. There is a little discussion, and I just want to bring this to your attention because it is in the textbook. It is something, of course, you need to keep in mind, but this is something you would have gotten a long time ago and in multiple science classes. Okay. When you're asking questions about adaptations, you need to make sure your questions you're asking actually approach the question you want answered. Okay. Meaning when you ask the questions, you need to be precise in your data collection and unbiased in your data collection. Okay. We know what unbiased means, yes? Okay. Do we know what we mean by precise? You want to be able to gather data that is not all over the place. Some questions will give you data that will be all over the place. If you modify the question such that it like hones in on something specific, it may make your precision much better. Okay. So just to bring that up, it's not something that any of you should be shaken by. You've all heard this before, but that of course applies to testing on adaptations as it does on anything else. Okay, so let's look at some. On the first page of the chapter, page 369, there's a picture of these flowers. Well, I'm going to show you a picture of these flowers here in just a second. Okay. Okay, it wipes off very easily. I wanted to make sure before I started writing on this screen that I could wipe off whatever I wrote on that screen. Okay. Okay. You will notice, it'll be easier once the picture comes up. You will notice these little white triangles on these flowers. Okay, little white triangles, little white triangles, little white triangles. Like I said, I'm going to have a picture here in just a second, but I wanted to point out those little white triangles. 6 petals, 6 white triangles. The white triangles are all pointed toward the center of the flower. So the points of the triangles are pointing toward the center of the flower. Okay, all right. Now you look at that and you assume, and there they are. Okay. You assume these little white triangles must have been selected for, they must do something. But what do they do? Well, we all know that flowers, if there's something associated with flowers, it's probably about the pollinators, okay? Probably about the pollinators. And so what did the researching scientists do? What the researching scientists did was this. They took these flowers, and yes, I did test to make sure that I could erase this off the screen. Okay. And so they blocked 3 of them out. Okay. Blocked 3 of them. All right. And then they had another test group where they blocked 5 of them out. And then they had another test group where they blocked all 6 of them out. Okay. So they had the control group, which had all of the white triangles visible, and then 3 test groups. 3 triangles blacked out, 5 triangles blacked out, all 6 triangles blacked out. Okay? Yes? Results? Anyone? Not in, the numbers actually were almost linear and almost in direct proportion to the triangles. Namely, you black out 3 of the triangles, you get about 50% of the pollination. You black out all 6, you almost eliminate entirely the pollination. Okay. Now, something else I'm going to share with you that isn't essential that you know for this example, but many pollinators, especially bees, can see in ultraviolet. You can't see in ultraviolet, but the bees can. And those white triangles shine brightly in ultraviolet as well. Okay. And so you're not just reducing the white signal, you're reducing the ultraviolet signal as well. Okay. And clearly, like I said, it has a tremendous effect on pollinator efficiency. Simple test. Easy to show. These are indeed advantageous to these flowers. Could barely get easier. Okay? Yes? Okay. Okay. The bird you are looking at. The bird you are looking at is something called an oxpecker. The suggested relationship between the oxpecker and the big mammals that it comes and visits on a regular basis was that this was a mutually beneficial relationship. Why? Because the oxpeckers were picking parasites off the large mammals and therefore getting a meal. And of course, the large mammals were benefiting because they got their parasites removed. Makes for a wonderful story. And there was anecdotal information that suggested this could be true because oxpeckers do indeed pick parasites off the big mammals. Okay? But of course, you need to test it. Okay? And so, how do they test it? Well, understand that testing this in the wild would be really hard. So, what they did was they used cattle. Now, cattle are not necessarily a normal host for the oxpeckers, but the oxpeckers appear to treat the cattle the same way they do any other large mammals out in nature in Africa. You with me? And so you're saying, well, how does using cattle benefit you? Well, because you can control whether the oxpeckers visit them or not. You can't very well go out on the African plains and chase the animals around and keep the oxpeckers away without scaring the crap out of the large mammals as well. Okay? It's kind of hard. So you use the cattle who are used to you. And so they had one corral where they let the oxpeckers do their thing and they made all their observations. And they had another corral where they would come out and every time an oxpecker would come, they'd go bang, 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 bang with some pots and pans. Okay? And the oxpeckers would fly away. So they had the control group without the oxpeckers, and they had the group where they let the oxpeckers visit and do their thing, okay? And indeed, they repeated this with 3 different pairs of corrals. So, I mean, that's not, sample size of 3 isn't tremendous, but it's better than 1, okay? And when you think about it, that's a pretty concerted effort to, look at 6 corrals with 6 groups of cattle in it. Anyway, what they found was, in one of the groups, there was no difference in parasite load between those that had oxpeckers and those that didn't. But one of them did have a beneficial, what appeared to be a beneficial relationship in the sense that the tick load on the oxpecker group was lower than on the control group. But in the third one, the tick load was actually higher on the oxpecker group than on the cattle, on the control one. So in other words, although yes, they will opportunistically remove parasites, it didn't appear that this was a general thing where it was a beneficial relationship to the large mammal they were sitting on. Plus, with careful observation, what the scientists saw as the oxpeckers picked off the parasite was that then the oxpeckers would sit there and peck at the wound and scissor with their beak and actually make the wound a little bigger and then come back and suck blood and chew on a little superficial tissue. Okay? Well, that's nice. Okay? So what was their conclusion? That this is not a mutualistic relationship. Yeah, they are more parasitic than anything. Okay, you got me? So the oxpeckers are getting a benefit and the large mammals are not necessarily getting a benefit because the oxpeckers are making at least as much use of their tissue as they are parasite tissue. Okay? You with me? And every single experimental group had more wounds on their skin than the control group. Meaning you let the oxpeckers in, there were more wounds on the skin. Okay? So that pretty much confirms they're being more parasitic than beneficial. Now, as an aside, however, they did find one other thing that maybe is actually beneficial, and that is that as weird as this sounds, oxpeckers also like cattle earwax. That was a good look on Taylor's face. Taylor going, okay. And so it was also true that the volume of earwax in the ears of those that had oxpeckers was lower than that of the control groups. Now, earwax is actually good in moderation, but we all know some of us have probably had issues with earwax buildup over time and know that you don't want it to build up tremendously. And so clearly the oxpeckers can stop the earwax from building up to a significant amount. Not a worthy trade-off. That's right. You'd still be more parasitic than anything. Okay. So again, here's another one. Anecdotal suggestion. Hey, look, they're in a mutualistic relationship. Well, guess what? Once you test it, that ain't the case. Okay. All right. Next one. Oh, I already had a picture of one. Pecking at the head of an anvil. Okay. Next one. This is actually the pictures from the original paper. And I think some of this is actually in your textbook too. What you are looking at here is a picture wing fly looking at a jumping spider. Now, this ain't the best picture, but this was done back in the 60s, okay? Or early 70s, something, okay? And you will notice the stripes on the picture wing fly. And something you can't see in this image, but I will show you a little bit in the next image, or the next example, is the actual behavior of the fly. This fly, when it lands and is in front of anything, it will sit there and wave its wings up and down. Okay? Like this. Okay? Up and down. All right? Now, it's helpful to know, and like I said, you'll see this in the next example. It's helpful to know that jumping spiders, when they encounter other jumping spiders, sit there and they will do this with their legs. Okay? They'll wave them around. This is a challenge to other males. It is a greeting to females. Okay. All right. You with me, everybody? Okay. And the basic idea was that it was thought that the pattern and the waving of the wings were beneficial in preventing the jumping spiders from attacking. Okay. Now, you have to test it. How do you test it? Well, they had 2 control groups and 3 experimental groups. The 2 control groups were intact picture wing flies and typical house flies with no protection of any kind whatsoever. Okay. And if you look at attack rates, you'll see that attack rates or even retreat by the spider happens with intact picture wing flies, but never happens with your intact house flies, because that's intact picture wing flies, that's intact house flies. And like I said, if you look at attack rates, you'll notice that intact picture wing flies never get, or basically almost never get stalked and attacked, although I don't understand how you can kill something if you don't stalk and attack it. Okay, maybe it's just you come upon it and surprise it and kill it. But the point is, you look at the picture wing flies compared to the house flies, and you basically are protected if you're an intact picture wing flies, and not protected if you're a house fly. Certainly not to any great extent. Now, what were their experimental groups? Well, their experimental groups were this. What they did was they cut wings off of both of the flies and stuck them onto the other species. Okay. Now you're going, how does that work? Well, you have to understand insects are not birds. This would not work if you were a bird. Okay. Insects, they don't have circulation. You can literally glue insect wings onto something that those wings don't belong to, and they can fly. As long as you get the costal veins nicely fused together, and so they can still fly. Okay. And why did we do this? Because this lets you know if it's the pattern or the waving or both. Okay. Because it turns out that if you cut the wings off and switch them, you will notice that neither of those groups, even though they would still wave, spiders don't retreat, and they certainly stalk and attack. You with me? And the house flies, even though they have the pattern, doesn't matter. The spiders don't retreat, and they're stalked and attacked. Okay. Now, what was the other experimental group? Well, the other experimental group was you cut the wings off and stick them right back on the picture wing flies. Now, why do we have this group? Yeah, exactly. For those of you who didn't hear what Christiana said, you have to find out if the process of removing and sticking wings back on has an effect in and of itself. So you cut the wings off and then you stick them right back on the same fly, and lo and behold, your responses are that it's unchanged. Because they still have both the pattern and the waving. And this experiment clearly shows it requires both. So it's not just the pattern, it is the pattern and the waving of the wings. Because these wave but have no pattern and they get attacked. These have the pattern and do not wave and they get attacked. So it requires that you have both the pattern and the waving. Yes, Gage?
For the housefly with nothing done to it, does the wing pattern, it seems to make it retreat a little bit more.
Well, I mean, the housefly intact makes it retreat none at all.
Yeah, and then the one with the swapped wings does it a little.
Maybe. Okay. This was done without standard deviation bars or anything, so I don't know about significance. I doubt that these values are significantly different from that value. So I would assume all three of these values would be considered the same. I would consider these two values would be the same and those three values would be the same. Here, this is a little bit more or less intuitive, but certainly all of this makes complete sense. Okay. All right. Now, I'm going to show you one more example that's basically like the one I just showed you, only this one involves moths. And well, crap. I'm not going to show you that one. Because I don't have access anymore. They've changed the rules. I guess I should have checked, huh? I'd gone with it for years on end and it never changed. So I thought I would probably be able to get to that one. Sorry about that. You will not be responsible for the number 3 underneath examples there. Okay. Because I just talked about the large mammals and oxpeckers and the tephritid fly, Zonosemata and Salticet. So 1 and 2, but not 3. Okay. All right. So we good? And you understand how the experiments that were done tested the adaptive value of certain things. And what we found was, well, in the case of the oxpeckers, not mutualistic, parasitic instead. But in the case of the picture wing flies, it requires that they both have the pattern and wave the wings. Okay. So sometimes we can do tests. Other times it's really difficult to do actual tests. Now, I'm going to start with 2 more experiments. One provides a test framework, but simply involves observing what your test subjects do. That's all it is. So we were doing experimental studies, what we just talked about. And now I'm going to talk about some observational studies. And in this case, I'm going to give you two examples, again, dealing with a similar phenomenon. And that is 2 examples on behavioral thermoregulation. Okay, what's behavioral thermoregulation? Let's start off with what's thermoregulation. What's thermoregulation? I already used that word earlier when I was talking about feathers. What's thermoregulation? It's being able to modify. It's not necessarily maintaining a constant body temperature, but it's being able to modify your body temperature around what the environment is doing. Okay. Now, obviously, if you're a homeotherm, and you know what I mean when I say homeotherm, yes? Are you a homeotherm? Are you a home? Yes, because what that means is maintaining a relatively constant body temperature. Understand that moment to moment, you are not precisely the same body temperature, but you're really damn close. Okay. Yes. And we all know how expensive that is, but obviously, again, the benefits outweigh the costs for those organisms that are homeotherms. There are only two groups, by the way. What two groups are true homeotherms? Birds and mammals. That's it. Okay. All right. So what I'm going to be talking about, of course, since it's behavioral thermoregulation. Now, let me point out, of course, that you behaviorally thermoregulate too. How do you behaviorally thermoregulate? Okay. You can put on your jacket when it gets cold. And what color is your jacket? Yeah, it's dark. Okay. All right. Or for that matter, it's sunny and kind of cool and you want to warm up, you can go lay in the sun or find a nice warm rock to sit on. We behaviorally thermoregulate too. And it actually makes sense because that can save us a little bit of energy. Because just because we produce internal heat doesn't mean we won't use external heat when we can get it. Okay. And of course, the flip side is also true when it's really hot. If we could get some cooling of some kind, we'll use that. Because again, it will cost you less energy to cool your body down. Okay. So if it's 102, you go jump in the pool. Okay. Yep. So be aware, of course, we behaviorally thermoregulate too, even though we are homeotherms. Okay. All right. For the organisms, the two examples they give in the textbook, one happens to be the roundworm Caenorhabditis elegans. Now, I do not expect you to remember Caenorhabditis elegans or even C. elegans. However, I will say this much. If you ever go into experimental, evolutionary biology, you'll probably play with Caenorhabditis elegans at some point. Because like Drosophila, this is a really easy to grow, really fast reproducing organism, which makes it great for laboratory studies. Okay, little roundworms. Because you can basically put them in a nutrient medium and they just take off with no problem. Okay. And so you literally have this big bowl of liquid with all these little roundworms swimming around in it. Okay. That's all there is. Okay. What the scientists did was they provided a temperature gradient on the bottom of the big vat of nutrient medium these were in. Okay. Now, I know it's liquid, and you should therefore understand that if it's liquid, that even if one end of the big vat is cool and one end is warm, that the liquid, of course, can mix some. But of course, the idea is you keep that to a minimum because it's in a very level place. It's in a laboratory where you're not shaking it around. And the little tiny roundworms aren't terribly great at mixing it themselves. And then what do? You look for where they gather. And where are they going to gather? At a temperature which is optimal for them. You should understand that although poikilotherms, those who are not homeotherms, and therefore whose body temperature can vary to some extent with the environment, still have a preferred temperature range that can be quite narrow. And why do they have that preferred temperature range? Well, here, I'll get to that by asking you this question. What's the big advantage? What's the really big advantage of being a homeotherm?
Relying on the environment.
Okay. You can subsist in multiple environments. I'll give you that. Okay. But the constant body temperature is a big deal. It's a big deal. So good, Christiana. High five. Okay. All right. What Christiana said was enzyme activity. Okay. Do not forget, every living organism requires its metabolism to survive. What's its metabolism? The collective of all the chemical reactions that keep it alive. That's your metabolism. Your metabolism shuts down, you're dead. That's simple. Okay. Now, yes, some reactions can take place on their own in the body, but the vast majority of reactions in the body require, Christiana, enzymes. And do those enzymes have an optimal temperature at which they work? Guess what your optimal temperature is for your enzymes in your body? It might just be 98.6 degrees Fahrenheit or 37 degrees Celsius. Okay. Now, actually, you can make some enzymes speed up a little bit if you heat up the body a little bit. There are two circumstances under which the body will heat up. What are the two circumstances under which the body will normally heat up? Exercise is one and fever is the other. Okay. And is there a reason why you like to warm the body up during both of those? The answer is because the enzymes in your muscles will work a little faster and a little bit more efficiently when they're a little warmer. Okay. And fever speeds up your metabolic rate, which helps you fight off the infection a little faster. Okay. But you have a basic optimum temperature, and that's why you have a constant body temperature. One set of enzymes optimally working all the time by far outweighs the cost of all that food you have to eat to fuel your body. Poikilotherms, not so benefited by that, but less energy required. Okay. But in some cases, some poikilotherms may have two different enzymes to run the same reaction because if their body temperature changes appreciably, this one works great at this temperature and this one works great at this temperature. And that's a cost. Okay. Which is why it's beneficial if you can, even as a poikilotherm, find your optimum temperature range in the environment. And that's exactly what you see. Again, I know the pictures are terribly tiny, but on page 379, what you see is how the roundworms distributed themselves in the medium they were in. And it basically is very few at the cold end, very few at the hot end. There's a peak in the middle. Imagine that. There's an optimum temperature range at which they survive. Okay? All right, I'll give you a slightly bigger example of a poikilotherm in behavioral thermoregulation. Okay, so that was, although you had an experiment, you're just observing what they do. Yes? All right, I'll give you another one, which is, again, you can't really experiment on this because of the detail required and the volume of space required. And what these scientists did was they looked at the behavioral thermoregulation in garter snakes. Now, how do garter snakes behaviorally thermoregulate? Where are you likely to find them in the morning? What was that? On a rock. Why are they doing that? They're heating themselves up. Okay? All right? This is true of probably most snake species where you find them in the morning. Okay. I found this out when I was in Costa Rica and I was out with my butterfly net and I come up on this big flat rock and there's a boa constrictor, the species boa constrictor sitting on that rock. And I went and threw my net over it and carried it back to camp and got it back to camp. And by noon, it had warmed all up and this, all the other students were coming back. And I said, "You got to see the snake I caught." And I reached in the bucket and I hear, and I pick it up out of the bucket. We ended up measuring, it was 8 feet long and it was this big around and I'm holding it by the head, but you can see from my expression on the many pictures that were taken of me, it's like, because it was strong enough to strike at people as they were going by, even though I was holding on to it. So, all right, I'm sorry. I really went off on a tangent there. Anyway, that's where you find snakes in the morning, okay, is on rocks. Where do you find them in the middle of the afternoon on a hot day? Okay, for garter snakes, it's not going to be in the water. It's going to be back under the rock, okay? So they're going to heat up in the morning. They're going to do their hunting in the morning after they heat up. And then as it gets hotter during the day, they're going to retreat, okay? Now, Where do they retreat to? Do they have a thermal optimum? What would be your answer to that question? Of course they have a thermal optimum. As I just said, all poikilotherms are going to have some thermal optimum. Okay? Yes? Yes? Okay. So, do they work it so that they can stay in their thermal optimum most of the time? And the answer is, interestingly enough, yes. No surprise there. Their behavior is adaptive. Do they crawl under small, medium size, or big rocks? Bryce said medium. He threw his hands to the side like, I'm taking a shot at this. Was that a shot? Okay, and why would that make sense? Aha! Well thought through, Bryce. Okay. And because if you measure the temperature under small rocks, if you measure the environmental temperature during the day, of course, it's going to go up in the morning and then peak in the late afternoon and then drop. And it does this day after day after day. Yes? Well, small rocks, what's the temperature going to do? That. Not enough protection. Big rocks, although you can find some snakes under the bigger rocks if there's space, big rocks are going to be too cool for much of the day. It never heats up significantly. So you find them under medium-sized rocks, okay? And how do you know? The scientists did this. They went around in the environment and they probably had to lift up medium-sized rocks and put them back, which of course is some disturbance, but that is exactly where you find like 95% of these garter snakes in the afternoon is under medium-sized rocks because it also does not dip way off at night either. There's some heat grabbing by the rock during the day, which keeps the temperature up overnight as well. Medium-sized rocks. Okay. So here's your hypothesis. They'll pick medium-sized rocks to roost under, and that's what they do. Okay. And using these observational studies, they were able to test it and show that it was a real phenomenon. Okay. All right. Now, there is something on in the next section, 10.4, where they talk about phylogenetic and independent contrast. I am not holding you responsible for anything having to do with phylogenetically independent contrast. Not that it's not a useful tool, but it's a pretty doggone complex tool, and it's one beyond what I want to cover in this course. Okay. Do be aware if you go on and you do any evolutionary studies and it talks about evolutionary phylogenetically independent contrasts, that there is some information about it in this textbook, should you happen to keep this textbook. Okay. But we will not do that. However, I will talk about the comparative method. Where am I in the clips here? Oh.
Cost benefit analysis.
Yeah. Okay. I'm going to do something else. I'm just going to summarize what I just said about the thermoregulation. Okay. Again, just to remind you, if you're trying to test if something is adaptive, because I put down 2 more comments on your review sheet, the organisms that choose particular temperatures more frequently than they would encounter than those temperatures at random in the environment. Okay. Are they choosing one set of temperatures? If they are, then that would suggest it's adaptive. Now, by saying that that choice is adaptive, what would that also mean? That those individuals who do that have higher, thank you, fitness. Never forget that if we are talking about an adaptation, it is a characteristic that, at least in today's world, gives those individuals a selective advantage, improves their fitness. Yes? Yes? Because that's what an adaptation is. Because I didn't really feel like I could start the comparative method. I didn't feel like I had enough time, so I wanted to just reiterate that. And so we'll start there next time.
Just like basically like walls away behind a cabinet, and then I moved.
Jesse, make sure you log out so I can close this.